Assalamualaikum warahmatullahi wabarakatuh. I would like to show you how to analyze the data simulation for drug stability experiment. So as I mentioned before, I explained before that in this experiment, the drug that we use is acetic salicylic acid or acetosal, and the degradation reaction is a hydrolysis. So this is the reaction of hydrolysis acetic salicylic acid or acetosal. So as we can see here, one molecule of acetosal will react with the water, one molecule of water, and produce one molecule of salicylic acid and one molecule of acetic acid. In this experiment, we take a sample by time. And we conduct the experiment in three kinds of temperature. So it's 40 degrees Celsius, 50 degrees Celsius, and 60 degrees Celsius. And each time we take a sample and determine the concentration of the degradation product, which is salicylic acid. So the concentration in the sample, it's the salicylic acid, not the acetosal or not the drug. How we calculate the amount of salicylic acid of each time? We use a standard curve, because from the spectrophotometer UV vis experiment or determination, we will get the absorbance value. So we use the absorbance value to calculate the concentration of the product, which is salicylic acid, and we already provide the standard curve. The standard curve here is y equal to 0.1288 plus 0.004, which the y is absorbance that we got from the spectrophotometer UV determination, and the x is the concentration of salicylic acid in ppm. And actually the data that we want is the concentration of acetosal by time. So we have to calculate. So we have to change the data from the salicylic acid into the acetosal that react with the water and produce the salicylic acid, and we have to calculate the acetosal by time, or the remain acetosal by time. So to calculate this one, we have to know the molecular weight of acetosal and also the molecular weight of salicylic acid. We already provide the value, and this is the data simulation that we provide to you. So from each experiment, from each temperature experiment, we got the number or the value of the absorbance of each sample. So in the temperature 40 degrees Celsius in 0 time, the sample show this absorbance, and so on in the temperature for 50 and temperature 60 degrees Celsius. So first, if we study the stability, first we have to know the reaction order. The reaction will follow which order reaction. So for this, we have to analyze the data. I already provide the table, so you have to fill in the table. So I will show you how to calculate or to fill in the table. First, in this table 2, data analysis at temperature 40 degrees Celsius, we got the absorbance data from each time, each sample. So how to calculate the amount of salicylic acid in ppm? Using this equation, we can get the number or the concentration of salicylic acid by time. So we calculate, because the y is the absorbance, and we want to know the x number. So x equal to the absorbance minus 0.004 divided by 0.128. So now we have the concentration of salicylic acid by time. So we just copy to the following cell. And the other analysis, is because in this experiment or in this study, we want the data of city in the zero order or all of the experiment. We need the number of concentration of acetosol by time, like for zero order, so we can calculate the number or the value of Ct. How we calculate the number of Ct? It's here, the initial concentration of acetosol minus by x. This is the x, but this x is the amount of the concentration of salicylic acid. If we want to know the concentration of acetosol by time, we have to know the concentration of acetosol that react with the water and produce salicylic acid. So how we calculate? This is the concentration, the initial concentration of acetosol, and we have to know the mole of the salicylic acid. How we know the mole of the salicylic acid is we divided the ppm or the concentration of salicylic acid by the molecular weight of salicylic acid. It's 138.12. So we get the mole of the salicylic acid, and the mole of salicylic acid is the same with the mole of acetosol that react with the water. So we change or we multiply again with the molecular weight of acetosol, and then we get the concentration or the ppm of the acetosol that react with the water. Okay, so it's 180.157. Okay, so this is the concentration of acetosol by time. This is the remain acetosol. And we also analyze this Ct to the log number because we want to know if the reaction will follow the first order reaction. As you can see here, if the reaction follow the first order reaction, so we have to make a regression between t or the time as a x-axis, and the y-axis or the y-series is a log concentration of acetosol by the time. So we have to analyze the data, the log 10 base of the concentration of acetosol by the time. So we get the log data, the log of the concentration, and we copy to the following cells. And to know if the reaction will follow the second order, so we have to analyze the data of the Ct. So this one, okay, this should be not minus, and we copy to the following cell. After we analyze the data, and then we see how the linearity of each order reaction. For the zero order reaction, we will make a regression of T versus the Ct. So we make a graph. So please insert the graph with a scatter type of graph. And then we select the data for zero order, add the data, and this is for zero order. Zero order, the x-axis will be a time, and the y-series is concentration by time. So now we have the graph of T versus concentration by time. To see the linearity, we can add trend line on the graph, and just display the equation, linear equation, and show the R square to know the linearity. And this is the equation and also the linearity, as you can see here. Maybe we can make the graph smaller. Okay, so this is for the zero order. We got the number of the R and also the equation. The equation means that the Y is the concentration by time or CT, and the X is the time, and the B is the mean K, as you can see in the zero order equation. So we can put the data from the linear regression to be here. So the A number is 58.071, and the B is the slope, which is minus 0.0069, and the R square is show the linearity of the graph. And then this is the number of K, or the value of K, because in the zero order equation, this equation will equal to CT equal to the B, the X is the T, and this is the B is also the mean K. So the number of K and the B is the same, just to minus it. And the next, we have to compare with the first order. So we insert the same type of graph using scatter. Okay. So we have selected data. Okay, because like this, so we have to remove all the data first. And add the new data for for the first order. For the first order, so the X is the same. The X is time. The Y is the value of the log concentration of acetosol by time. So this is the graph. We can make it smaller, or maybe we can add the trend line to know the number of R square. Put the linear and display the equation, and also display the R square on the chart. And we know the R number, or the R value, and also the equation. So the equation will be the Y is the log concentration, and the B, this is the B number, and this is the A number. The B number, or the B value, is equal to the mean K per 2.303, because we are using log concentration, and the X is still the same, it's the time. So the A number is 1764, and the B is minus 0.00005, and the R number 9991, and the K is the number of B sorry. The K is the number of B multiplied with 2, 3 or 3. The minus B, because in the equation is minus K2. So this is the number of the value of K if the reaction follow the first order. How we see the linearity of the second order reaction? So for the second order reaction, we can make a graph 2 with the data is, we can move the graph because if we cannot see the data. Okay, select the data. For the second order reaction, second order, the x-axis will be the same. It's still time, and the y-series is the per concentration of acetosol by time. And then we get the graph here, and then we can put the trend line. So just click the data and then add trend line. Click the linear here and display equation and also the R square. Then now we get the data of the R square. So we can make it smaller. So we get the second order reaction, and this equation means the y is the 1 per concentration by time, and the x is still the same, the time, and the b will be k, because in this equation 1 per concentration by time equal to 1 concentration per initial concentration plus k multiply t. So this is also the value of the k, the b number, and this a is 1 per initial concentration of acetosol, and this is the number of R square. So we can just put here, put in this table. So okay, I cannot see the equation. Okay, this one. The A is 0.0172 and the B is 0.000002 and the R is 0.999, and the K will be the same number with the B, so it's 0.000002. Okay, so in this experiment in 40 degrees Celsius, we already got all the data, and from the linearity analyzed, we can decide that in the temperature of 40 degrees Celsius, the degradation of acetosol follow the zero order reaction. So I will mark it, and then we have to do the same thing, the same calculation and same analysis in the data of the experiment in temperature 50 degrees Celsius and 60 degrees Celsius. Yeah, we have to fill in the blank each table, and if we already got all the reaction order each temperature, so we can put the data here, so we get the data between the 1 per temperature, so it should be temperature. But in K, in absolute temperature. So we got this number. So this is 1 per 313, and this is 1 per 323, and this is 1 per 333. And how about the K? The K we can get from the previous data. For example, for the first temperature, 40 degrees Celsius, the K is 0.0069, as you can see here in the first analyzing here. And I will put the example. For example, in the 50 degrees Celsius, we got the K, the number of K is 0.033, and 60 degrees Celsius, we got the K value is 0.09. So to know the K, or the rate constant in the room temperature, we have to analyze the data using the Arrhenius equation, which the Arrhenius equation is log K equal to log A, mean AR. AR is activation energy, divided by 2.303 R, and multiply with 1 per T in Kelvin. So to know the K in 25 degrees Celsius, we can make a regression using these three data, which the X series is the 1 per K, and the Y series is log K. So we can make a graph here using scattering graph, and select the data. So this is Arrhenius equation, which the X series are the 1 per temperature in Kelvin, and the Y series is log K. So this is the data here, and we can add trend line to know the equation that we got from this regression line here. Add trend line and then display the equation on chart. So this is the equation which equal to the Arrhenius equation. So the Y will be the log K, and the B of this equation will be the minus EA per 2.303 R, and the X is 1 per T in Kelvin. The A number, the A value here in this equation is equal or the same as the number of log A, and this is the R square number. It's quite good, 0.9 something. So from this equation we can calculate the amount of log K when the temperature is 25 degrees Celsius. So from this equation you can calculate the value of the K in 25 degrees Celsius. So just put the X number by the 1 per 20 degrees Celsius, but it should be in Kelvin. So 25 degrees Celsius plus 273, so it will be 1 per, the X will be 1 per 2, so we can calculate using this equation to know the log of the K or the rate constant of in the temperature 25 degrees Celsius. So just put in the substitute into the equation. So it's minus 5,824.1 and multiply by 1/298. You can make a bracket to make sure, and plus 61 for this. So this is the number of log K at 25 degrees Celsius. To know the number of K, you can calculate. You can anti-log this number, and then you put the K on of 25 degrees Celsius, and then you can use this K to calculate the T19, and also you can calculate the AR. Okay, after you get the value of K at the temperature of 25 degrees Celsius or room temperature, you can calculate the value of T90, but you have to choose the suitable of the formula of T90, because you have to choose the order reaction, because different order reaction will have the different formula for T90. And if your order reaction use the formula that involve in the number or the value of initial concentration, you should use your very initial concentration, not the initial concentration with the same condition with the sample. For example, in this experiment, for the first, you have to weigh 0.1 gram and then dissolve in 500 milliliters. So that's the initial concentration of the drug. So use that initial concentration, not the initial concentration of the same condition as the sample. Okay, I think that's for how we can analyze the data simulation for this experiment. I think it's can be understand. So I will close this explanation by reciting Hamdalah, Alhamdulillahirabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh.